Good day, students. Today's topic is moment of forces. Moment is the product of a force and the perpendicular distance of its line of action from a fixed point. Its SI unit is Newton meters. N for Newton, M for meters. Why? Because moment is force multiplied by distance. Force is measured in Newton, distance is measured in meters. Let us take the example of a door. If you are applying a force at the extreme end of the door, that's why the handle of the door is usually located at the edge. So when you apply a force at this edge of the door, and the distance between where you are applying the force and the pivot is D, then the moment you are applying to the door is your force F multiplied by your distance D. Let us take an example. Consider a situation whereby a boy applies a force of 80 Newton on a door and the length of the door is 0.5 meters. Now, what is the moment produced? So you say, since the force is 80 Newton and the distance is 0.5 meters, you just say your moment is equal to force multiplied by the perpendicular distance. Your force is 80 Newton, your force is 80 Newton, the distance is 0.5 meters. 80 multiplied by 0.5, we get 40 Newton meters. And this is the moment produced by the force. To gain better understanding of moment, we have to understand what we mean when we say center of gravity. When we say center of gravity, what do we mean? Center of gravity, this is the point where the entire weight of a body appears to be concentrated. Wherever the entire weight of a body appears to be concentrated, we take that part of the body as the center of gravity. How do we find the center of gravity of a body? Let us take, for instance, let us consider this book, for example. You can see this book here. The center of gravity is the point where the weight appears to be concentrated. So if I place my hand at this edge, and I place my hand here and I leave the book will fall. Okay? If I place my hand here, okay, the book will fall. But if I successfully locate the center of gravity and I place my hand on the center of gravity and I try to position the book this way, then you notice that the book stays, okay? Even if it's not perfectly balanced because I'm not getting the center of gravity perfectly. If I reposition my hand in order to get it perfectly, I think I have a better position now, okay? Why? Why is the book balanced? Because I've located the center of gravity of the object. So let us consider a situation like this. Consider this object. Let us consider a beam. Okay? So if we use a knife edge to support this beam at the very center of gravity, then the beam will be balanced. But if I don't support it at the center of gravity, if I support it at this end, for instance, then the beam will not be balanced. Why? Because the center of gravity of the beam is at the center. That means the weight of the beam is located at the center of gravity. Now, the center of gravity, that's where the weight is located. And the knife edge, that's where the pivot, we consider the pivot to be at the knife edge. Now, if the pivot is here and the weight is here, then there is a moment, and that moment is equal to the force multiplied by the distance between where this force is applied and the pivot from the definition of moment. It is the product of a force and what? The perpendicular distance of its line of action. So this is the line of action of this force, okay? It's acting along this line. Okay, so we have our force, and the force is equal to the weight. Do not forget that weight is defined as the force on a body due to gravity. Okay, the force due to gravity is equal to weight. So weight is also a force. That's why weight is measured in Newton. So the force here is the weight of this thing, and the distance is the distance between the center of gravity and the pivot. So there's a distance, hence there's a moment that is produced, there's a resultant moment. Okay, but if we successfully place the knife edge at the very center of gravity, if we place the knife edge here, okay, that means this is the center of gravity. So the pivot is at the center. Okay, so the pivot is here, and the center, this is the center of gravity of this object. Hence, the weight is acting downwards. The weight is acting at the pivot. Okay, that means there's no resultant moment. Okay, but if we shift, the weight is acting here, but if we shift the pivot to this position, okay, that means now there is a distance between the weight and the position of the pivot. And whenever we have a distance, then we can calculate the moment as the force multiplied by the distance. That's why whenever I support this book at a point other than the center of gravity, okay, if I support it here, what will happen? Then the book will fall. If I support it here, then the book will fall. Why? This is not the center of gravity. This is where the center of gravity is. So if I support it here and I remove my hand, then the moment causes the book to fall. But how do you locate the center of gravity? What are the steps that you must take when you want to find the position of the center of gravity of an object? That is what we'll be talking about now. How to find the position of center of gravity. Our topic is still moment. Now, when you want to find the center of gravity, what will you do? Let me take, for example, this circular object. If I want to find the position of the center of gravity of this circular object, I will produce a hole and make it hang freely. Okay, I will produce a hole, I will hang it with a sharp object, and I will allow this object to hang freely. Okay, once it's hanging freely, let me place it on the board so you can see it clearly. So once this object is hanging freely, then I'll produce a vertical line. Okay, I'll produce a plumb line. A plumb line. That is a line that goes straight into the center of the earth. Okay, it's a line that goes straight into gravity. I produce a vertical line. Okay, and then I will hang it on another hole. Okay, so that it can hang freely. Okay, and I'm doing the same thing. I produce a vertical line. Where these lines meet is the position of the center of gravity. Okay? Wherever these lines meet is the position of the center of gravity. That means I can successfully hold it at this point. If I can place my hand at this very point successfully, then this object will hang freely. Why? Because there's no resultant moment. Okay? I'm holding it at the center of gravity. But if I shift my hand away from this center of gravity and I want to hold it, once I remove my hand from the other side, the object will fall. Why? Because there's a resultant moment. Okay, this is a circular object, this is the center of gravity. So once I place the knife edge here, the object stays balanced. But once I shift the knife edge, okay, or the pivot, and I put the pivot here, and this is the center of gravity, now there's a distance between the knife edge. Okay, there's a distance between the knife edge. Okay, I call this knife edge because it's meant to be as sharp as a knife. Okay, or you call it pivot. So if there's a distance between the knife edge acts as a pivot, that's why you can call it the pivot. So if there's a distance between the center of gravity and the pivot, there's a distance, and then you have the weight of the object, then there is a resultant moment, which is the force multiplied by the distance. But if the knife edge or the pivot is located at the center of gravity, then there is no resultant moment, and the object will be balanced. Let us take other examples. Let us find the center of gravity of objects of various shapes. Let us deal with a rectangle. Okay, I produce a hole here. Yes, I'll produce a hole here and I'll allow this rectangle to hang freely. Okay, so once I do this, and then I'll draw a vertical line, a line that runs straight through the center of the earth. Okay, so I'll hang it at another location. I'm hanging it here. Okay, and I want to produce my vertical line again. So I'll produce a line that goes straight into the center of the earth. Where these two meet gives the position of the center of gravity. Okay, you may decide to use 3 lines. Okay, let me hang it again using a third point, and I will place it. I'll make it balanced. Okay, once it's balanced, then I'll draw my vertical line. Where these 3 lines meet is the center of gravity. That means I can successfully hang it here at this point, and the object will be balanced. Why? Because my hand is at the center of gravity. That's the effect of using a single force to balance an object at the center of gravity. Now I want to find the center of gravity of this triangle. Okay, the shape here is a triangle. What will I do? The same thing. I will hang it here. Okay, I will place it on the wall, and then I will produce a vertical line that will enable me to locate the center of gravity. Okay, I'll hang it at another point. Okay, I'll make sure it's free. Okay, I'll make sure it balances. Okay, so when it's not oscillating, I produce my vertical line. Ideally, this line is supposed to be perfectly straight in order to get the exact location of the center of gravity. Okay, I'm producing a third line. Okay, I didn't get this perfectly. Anyway, this 3 of them are supposed to meet at a point. Okay, yeah, if I'm doing this in a laboratory with appropriate equipment, they are all expected to meet at one point. So if I place my hand there and place it like this, then this triangle will be balanced. You can see that the distance from here to the knife edge is smaller than the distance from here to the knife edge. Why? Because the center of gravity is closer to this side. You know, it is not, looking at it, we have more of the volume here, more of the area here compared to the top. That's why the center of gravity is lower, okay, than, that's why the center of gravity is closer to this edge, okay. So if you place it here, the object will be balanced. This is the effect of center of gravity on the stability of various objects, okay. You can try this object too. We can try objects of various shapes. Okay, so I'll just be quick with this one. I produce a vertical line. My vertical line is falling outside. It's fine. Let me try this position. I produce a vertical line. I come this way. I produce a vertical line. I come this way. I produce another vertical line. Wow. This doesn't look good. Anyway, let me just try to find, well, since this is a piece of paper, it's not firm, okay? But if you try this with wood, yes, if you cut wood of this shape, the center of gravity is here in this case. The center of gravity might eventually be at a point outside the shape. Let's assume I cut this further and I make this shape to be more hollow. The center of gravity will eventually be at a point like this. So it's not every time the center of gravity will be in the middle of the object, okay? Yeah, but in that case, that simply means if you produce a force, if you hang it here, this way, then it will be balanced. That's what it means. Oh, it's not balanced yet. Okay, if you hang it here, it's meant to be balanced. If you hang it this way, but if you are turning it this way, and the center of gravity is outside at this point, that means you cannot successfully hold it at a point. It will sag down. This example could have been better if we were using a solid object, but I'm sure you understand the concept of center of gravity and the effect of placing an object on a knife edge when the knife edge is on the center of gravity and when the knife edge is not at the center of gravity. This brings us straight to equilibrium. When you hear the word equilibrium, what comes to your mind? Equilibrium is the degree of stability of a body. There are three types of equilibrium. The first one is stable equilibrium, unstable equilibrium, and neutral equilibrium. So I will remove my face so that we can focus on the lesson. When you hear stable equilibrium, what comes to your mind? Now, in the case of stable equilibrium, when you apply a little force, the object tends to return to its equilibrium position. Let us consider a ball that is in a bowl. So if you apply a little force, you push this object, you push it so that it goes to this position, what happens? It will return to this initial position, okay? So that's why we said it's in stable equilibrium, because when you push it slightly, when you slightly displace it, it tends to return to its original position. Though it might come, oscillate, and then finally settle at the original position. That's why we say it is in stable equilibrium. But when an object is in unstable equilibrium, we can consider an example like this. An object that is placed in an inverted bowl, okay? Or a bowl that is upside down. Okay? So this represents a bowl actually. So when you place it in an inverted bowl, what happens? Now you can place it here and make sure it's balanced. That means it's in equilibrium, but it's an unstable equilibrium. Why? Because when you apply a little force in order to displace it to this position, what happens? It is now on a ramp or a slope, and gravity would make it to keep moving. It keeps moving further away from the supposed new position. But what about neutral equilibrium? You have the object in this position. When you displace with a little force, it moves further away and stays in its new position. That means it is neutral equilibrium. It is not biased to be stable or biased to be unstable, but it is neutral. Okay? Let us take another example of objects in equilibrium. Let us take another example of stable equilibrium. Let us consider a cone that stands on its wide base. This cone is in stable equilibrium because when you push it slightly, it might tilt a little bit and then return to its original position. But what about an inverted cone? Consider a cone that is upside down. Though in practical situation, it is impossible to make a cone like this to be in equilibrium. You cannot stabilize it. But let us assume you successfully stabilize it. Then it will be in unstable equilibrium because any little force you apply on it, the cone will move further away. Okay, it will move further away. That's why we consider this to be very unstable. That's why it's called unstable equilibrium. What about neutral equilibrium? Consider a cone that lies on a slant face. Okay, so in this case, when you apply little force in order to push the cone forward, it just rotates forward and stays in its new position. Okay, so this case we don't consider the cone to be biased to be stable or unstable, but it's neutral. That's why we call this neutral equilibrium. Let us consider a practical situation where we have stable equilibrium, unstable equilibrium, and neutral equilibrium. Look at this. This is a bolt, right? Good. We are considering different orientations of a bolt. Now, if you look at the first one, you can see that in this case, this bolt, is it stable or unstable? This can be considered to be an unstable equilibrium. Because when you push it slightly, what happens? The bolt falls down, okay? What about this one? If you push it slightly, with little force, if you push it with little force, what happens? It will tilt slightly. Once you remove the force, it returns to its original position. That's why we consider this to be in stable equilibrium, okay? And in this case, this is considered to be neutral equilibrium because when you apply little force, it will just when you apply little force, okay, it will just tilt to this side, and then it will eventually rest on this side. This side will eventually rest on the ground. Okay, that's how you consider this to be in neutral equilibrium. So that is a practical application of the three types of equilibrium. Now we'll be solving some questions on this. Okay, before we solve questions, we talk about the conditions that must be met before a body can be considered to be in equilibrium. What are the necessary conditions for a body to be in equilibrium? There are two conditions, okay? Conditions necessary for a body to be in equilibrium. There are two of them. Number one, the resultant forces on the body must be equal to 0. What does that mean? Let us consider this beam, for instance, that rests on this knife edge. Okay, I've been talking about beam so many times. Let us use example of a meter rule. You know what a meter rule is? A meter rule is just a very long stick whose length is 1 meter, and then it is uniform. Okay, that means the width is uniform from beginning to end. The first mark is 0 centimeters, and the last mark is 100 centimeters. The middle of the beam is calibrated as 50 centimeters. This is a uniform meter rule. Now, if you place a knife edge at the 50 centimeters mark, okay, you know, because the knife edge is at the center of gravity, the weight of the meter rule is at the center of gravity. That's the 50 centimeters mark, right? Good. Also, the pivot or the knife edge is at the 50 centimeters mark. What does that mean? The weight acts downwards, okay, the weight of the meter rule, and the knife edge is producing a reaction. You know, action and reaction are equal and opposite to each other. Okay, so the knife edge produces a reaction in order to withstand the weight of the meter rule. If the knife edge is not producing a reaction, that means the knife edge will then collapse. An example is if you use sand, if you use quicksand, if you just produce a pile of sand, okay, to form a knife edge, and then you place a very heavy object on it. Let us assume you place, you remove the engine, or you place your television on it. You place your TV on a knife edge that is made of quicksand. What happens? Of course, this is modern days television, but let's just assume you place a very heavy television on a knife edge that is made of quicksand. What happens? This knife edge is too weak to provide a reaction. Hence, the knife edge will collapse. Okay? The knife edge will collapse completely, and you have your TV on the ground. Okay? So that's what happens when reaction is not enough reaction is not provided. But your knife edge made of wood or a metal, a very solid object, is produces the reaction that balances the weight or the action of the meter rule. Hence, the meter rule will be stabilized. That's what we mean by the resultant forces on the body must be equal to 0. In this case, the knife edge or the quicksand collapsed because it could not produce enough reaction. So it fell until it was able to produce enough reaction. Okay, yeah, that's why if you have a cup and then you put a metallic object, okay, or you put stone in this cup, what happens? The water in this cup, in this stone, cannot provide the reaction. Hence, the stone continues to go deep down and it sinks to the bottom of the cup until it meets a solid surface that can provide the reaction. Okay, so the stone will continue to move in the water until there's a reaction that can balance the action force. So that's what we mean when we say the resultant forces must be 0. Until the stone gets here, this is when the resultant forces is 0. Here, the resultant force is not 0 because the weight brings it down. Here, the resultant force is not 0 because the weight acts downwards, okay? The weight acts downwards, though there's an up thrust due to the liquid, but the up thrust is less than the weight. That's why the stone will continue to move downwards till it gets to the bottom of the cork here. Okay, so that is the effect of this statement. The resultant forces on the body must be zero. When the resultant force is zero, then the object is not moving downwards or upwards. It stays in one position. But there's another condition. An object can be in one position and then starts rotating. An example, no, that's not an example. An example are the blades of your fan. Okay, your ceiling fan. It stays in one position, but it continues to rotate, right? Yeah. But in this case, if you want to consider it to be in static equilibrium, then the resultant torque must be zero. Or you say the total clockwise moment must be equal to the total anti-clockwise moment about any point. What do we mean by that? In this case, the total clockwise moment is equal to the total anti-clockwise moment because this beam is not rotating. But let us assume you decided to place this knife edge at the 40 centimeters mark. Let this be 40, let this be 30, let this be 20, let this be 10 and 0. Let's assume you decide to place the beam at the 40 centimeter mark. If you place the knife edge rather at the 40 centimeters mark, what happened? Let us assume the weight of this metal roll. Let us assume the weight of this metal roll is let us assume the weight is 200 Newton. This is unreasonable. Sorry, that's unreasonable. That's unreasonable. Let us just assume the weight of the metal roll is 20 Newton. What does that mean? Now that the knife edge is not at the center of gravity, then there's a resultant moment. What is the resultant moment? It is a resultant clockwise moment. What does that mean? It means this thing will rotate in a clockwise direction. Why is it rotating in the clockwise direction? Because moment is force multiplied by distance, and the force is the weight of this metal roll. The weight of the metal roll is 20 Newton. The distance, that's the distance between this 40 and 50 centimeters mark. What's the distance here? 50 minus 40 will give you 10. Okay, the distance is 10 centimeters. Okay, the force is equal to the weight, which is 20 Newton. The distance is the difference between 50 and 40. You know, the distance between the force, okay, and the pivot. So the distance is 50 minus 40, which is equal to 10 centimeter. You know, we have to convert from centimeter to meter by dividing by 100. That means your distance is 0.1 meters. Hence, the resultant moment is force times the distance. The force is the weight, which is 20. The distance is 0.1 meter. 20 multiplied by 0.1 meter, we have 2 Newton meter. So there's a resultant moment in this situation. Okay, and the resultant moment is a resultant clockwise moment. Okay, why? Because the resultant force is on the right hand side. So here, the total clockwise moment is not equal to total anti-clockwise moment. What's the anti-clockwise moment? There's no anti-clockwise moment. Why? Because there's no force on the left hand side. So this beam is not in equilibrium. Okay, but if we shift this beam to the center, and the beam is resting at the center of gravity. I mean, if you shift the knife edge rather to the center, then we consider this beam to be in equilibrium. That's what we mean by saying the total clockwise moment must be equal to the total anti-clockwise moment about any point. Okay? Or you just say the resultant torque must be zero. Torque also refers to moment. This is the resultant torque. The resultant torque is not zero. Hence, the body is not in equilibrium. Okay? But in a situation whereby it's resting on the center of gravity, okay, moment is force times distance. Okay? The weight is 20 Newton. Okay? So, if you want to calculate moment, in this situation, the moment will be the force multiplied by the distance. The moment is the force multiplied by the distance. The force is the weight, which is 20 Newton. The distance is 0. Yeah, the distance between the center of gravity and the knife edge is 0. Why? Because the center of gravity, that is where the knife edge is resting. So if you multiply 20 by 0, you get 0. So the resultant moment is 0. That's why the body is considered to be in equilibrium. Let us solve some exam questions on moment to know how prepared you are and to know how well you understand the topic. I'll wipe up the board and I'll put some questions here and we are going to solve these questions together. Question number 1. Consider a situation below. Consider this uniform meter rule. Okay, this 0 centimeters mark. This is the center. I can take this at the center. This meter rule does not look like a uniform meter rule. Okay, I think it now looks like a uniform meter rule. Okay, yeah, so this uniform meter rule, this is the 50 centimeters mark and this is the 100 centimeters mark. Now, if you place a knife edge at this point, okay, and it balances horizontally. Now, if you apply a force of, this is 10, 20, 30, 40, at the 20 centimeters mark, if you apply a force of 80 Newton, then what force can we apply at the 90 centimeters mark? This is 90. Calculate the force that must be applied at the 90 centimeters mark. So this is a standard exam question that you might be asked. What will you do? First of all, the question says that the uniform meter rule is in static equilibrium. That means it is not moving. Okay? Yeah. So if this uniform rule is in static equilibrium, when we say static equilibrium, that means the object is not moving. Take note that the resultant forces must be 0. You know, force is equal to mass times acceleration. So when force is 0, then one of these must be 0. Is it mass? Is it acceleration? Every object has a mass, okay? Matter is anything that has mass and occupied space. So your object has a mass. So if the force is 0, then it is the acceleration that must be equal to 0. Good. So for an object to be in equilibrium, the acceleration of the object must be 0. Now, if acceleration is 0, it means velocity is constant. Okay? That means your velocity is either 0, okay, or a constant value. You know, 0 is also a constant value. As long as the velocity is not changing, then the object is in equilibrium. This simply means that a ball that is moving at a constant speed of 5 meters per second and the direction is not changing, it keeps moving at the speed of 5 meters per second, this ball is in equilibrium. Yes. The comets in space, these are stones that are moving at a very high speed. The speed can be as high as 10,000 meters per second. As long as this speed does not change, they are considered to be in equilibrium. But the other kind of equilibrium is dynamic equilibrium. That means the objects are moving but at a constant speed. But whenever you hear static equilibrium, that means the object is not moving at all. Okay, it is not moving. That means the speed is 0 and it is not rotating. That means the resultant moment must be 0. So let me finish up. I'm done with this explanation of an object being in equilibrium. Okay, that means it moves at a constant speed. The speed can be 0 and the speed can be any value. As long as there is no acceleration, then the object is in equilibrium. Now, as for static equilibrium, that means it's not moving. Okay, so the resultant force is 0. That means if you add these forces together, they balance up the reaction produced by the knife edge. Okay, so let's not focus on the forces. Okay, Yeah, let's focus on the what? On the moment. If this object is in equilibrium, that means the resultant, that means the total clockwise moment must be equal to the total anti-clockwise moment. So we write here total clockwise moment must be equal to total anti-clockwise moment. What is the clockwise moment? The clockwise moment, this is the force that's producing the clockwise moment. The force on the right tends to make this beam to rotate in the direction of the clockwise moment, okay? We have a knife edge here, you have the beam here, okay? Yes, this is the meter roll, this is the knife edge. If you apply the force here, then the beam tends to rotate this way. So the clockwise moment is produced by F multiplied by the distance here. What's the distance from here to here? 90 minus 50, that's the distance, okay? Okay, let us call this our D2. Let's call this distance our D1. Let's call the force here our F1. Let's call the force here our F2. Okay? So, according to the principle, total clockwise moment, what's your clockwise moment? F2 times D2. So you say F2 times D2 must be equal to total anti-clockwise moment. That's F1 times D1. Okay? Good. So that's it. F2 times D2 must be equal to F1 times D1. What is F2? We do not know it. So we write F2. What's D2? 90 minus 50. 90 minus 50 gives us 40. Okay? Okay? Or you just put it here, 90 minus 50. Then F1 is 80 multiplied by what is D1? That's the distance from here to here. How do you get this distance? 50 minus 20. 50 minus 20. Easy. So we have F2 times 90 minus 50 gives us 40. Is equal to 80 multiplied by 50 minus 20 gives us 30. So that means we have 40 multiplied by F2, that will be 40 F2 is equal to 80 multiplied by 30 will be 2,400. To get F2, since 40 F2 is equal to 2,400, to get F2 we divide both sides by 40. So 40 will cancel out 40. On the left hand side, we left it F2 is equal to 2,400 divided by 40. 240 divided by 40. 200 divided by 4, that will be 50. 200 divided by 4, that will be 50. 40 divided by 4, that will be 10. So your answer will be 60. 60 Newton. That simply means a force of 60 Newton will be needed to balance this beam, okay? So when the force here is 60 Newton when the force here is 60 Newton, then the beam will be in equilibrium. May we solve another example? Yes, let us solve another example. Now we want to solve an example that involves more than one force. Okay? Yeah. So you want to solve an example that involves more than two forces. But before that, let us identify the direction of forces that produce the clockwise moment and the direction of the forces that produce the anti-clockwise moment. Now look at this beam here. This is the knife edge at the center, okay? Okay, let me just make it clear that the knife edge is at the center. Centimeter, centimeter, centimeter. Now let us assume no force is acting on this beam, okay? On this meter roll. That means the meter roll is in equilibrium, right? If we do not apply any force at any edge, then the meter roll is in equilibrium. Now, if we apply a force of 50 Newton at the 0 centimeter mark, let me make it clear that it's 0. If you apply a force of 50 Newton at the 0 centimeter mark, in what direction will this beam rotate? With the meter roll? What direction would the meter roll rotate? In an anti-clockwise direction. Okay, so it's rotating in an anti-clockwise direction. Now let us assume that you decide to apply this force here, okay, 50 Newton. In what direction will this rotate here? It will rotate in a clockwise direction. Why? Because the force is on the right hand side, okay? Yeah. So you have a beam on a knife edge, you apply a force here on the right hand side, it will rotate in a clockwise direction. Now let us assume that we now apply the force upward. Let me put the 0 centimeter mark here. Now we are applying a force of 40 Newton, okay, in an upward direction. What will be the moments produced by this upward force? If you apply an upward force, you see it is rotating in an anti-clockwise direction, okay? The marker is rotating in an anti-clockwise direction. So this force will produce a counterclockwise moment. What if we apply the force in this position, an upward force here? An upward force at this end will produce an anti-clockwise moment. Sorry, this is producing an anti-clockwise moment, okay? While the one here is producing a clockwise moment, okay? In the absence of this force, the force applied here will be producing a clockwise moment. Let us solve an example involving two forces. Now I'm using this same knife edge, okay? So I'm applying a force of 0 centimeter. I'm applying a force of 40 Newton at the 10 centimeters mark. I'm also applying another force of 50 Newton at the 30 centimeters mark. What will be the force that will apply at the 80 centimeters mark to balance it? Good. So this is a standard exam question. Calculate the force that must be applied here to balance it. What's the formula you use? Total clockwise moment. Total clockwise moment must be equal to the total anti-clockwise moment. Must be equal to the total anti-clockwise moment. Now, what's producing the clockwise moment? This force and this distance. Okay? Okay? So let us call this force our F1. We call the distance here. We call the distance from here to the knife edge. We call it our D1. Okay? The distance between F1, these are F1. The distance between F1 and the knife edge is called our distance D1. Okay, so I'm using this dotted mark to show you that I'm picking the distance from here to here. Also, the distance between our force, we call this our F2. Okay, the distance between our F2 and the knife edge, we call it D2. Okay, and the force we are looking for, let's call it F3. Okay, the distance between the force we are looking for and the knife edge, let's call it our G3. Now, what's the total clockwise moment? This is the force producing the clockwise moment, F3 and D3. That means F3, D3 must be equal to total anti-clockwise moment. What's the force producing anti-clockwise moment? These two forces are producing anti-clockwise moment. F1